Hey everybody, this is Mr. Schaefer. Thanks so much for checking out my YouTube channel and for looking at a number of these videos with me. So far, we have wrapped up our year with calculus, and so we're getting ready for the AP exam, which will be upon us shortly. To help you prepare, I have a series of videos that I'm working on right now, including this one today, that's going to take you through a walkthrough of some sample test questions, some free response questions. And the first video here today is going to cover 2 calculator FRQs. So have your calculator with you and grab a pencil. You can work these out with me together. This is a little video walkthrough. I'll go through it pretty quickly, but again, kind of budget 15 minutes per FRQ. We'll do 2 of them, so 30 minutes for these 2 here today. Let's begin. A bug is walking along the x-axis on the interval 0 to 5. The bug's velocity is given here by this equation, and the units are meters per second. So if I'm annotating my work, I'm going to underline the units and pay very close attention to whenever they're listed. This is going to be an algebraic approach. A function is explicitly given to me here in the problem, and there it is, velocity of this bug. So it sounds like a particle motion kind of idea with physics concepts, acceleration, velocity, maybe position later on. Part A says, again, look at this with correct units. Good thing I marked those earlier on. Find A of 2, acceleration of the bug at time 2, and then determine if the bug is speeding up or slowing down. Well, first of all, A of 2 is the derivative of velocity. So v prime of t is the same thing as acceleration. So what I would maybe do with my calculator is use math 8 on the TI-84s and enter this velocity function in, but type in for the value of t when it is 2. So again, it's going to look like this, d dx of my velocity function, and I want to know what that equals when time equals 2. So on my calculator, I get a value for a of 2 of negative 7.005, and that's meters per second, or meters per second squared because it's an acceleration value. Now, to determine if the bug is speeding up or slowing down, we also need to analyze the velocity at that time too. So what is velocity at 2? I'm going to use my calculator, and maybe if I have this plugged into y1, I can simply recall y1. So I'll hit y1 on my calculator, parentheses 2, that equals the velocity at time 2, and my value was negative 1.806 units, again, are meters per second velocity. So what does that tell me? I have a negative acceleration and negative velocity at time 2, and since both acceleration and velocity are negative, then that tells me that the bug is actually speeding up. So I'll say the bug is speeding up at time t equals 2, and then when it says to, oh, it doesn't say here to give a reason for your answer, I will though, comma, because a of 2 is negative and v of 2 is negative. Both acceleration and velocity have the same sign. Okay, letter B. At what time or times t does the bug have an acceleration of 0? And show the setup. So it's a calculator problem, but we want to make sure that we always show the setup. Anything that we're typing in the calculator, an integral expression, an equation to solve, some kind of function, make sure that it gets written down on your FRQ. So in this case, I'm going to know when is a of t, which is v prime, equal to 0. So I'm going to use my calculator to find the solutions, and I'm going to have 2 different times between 0 and 5. 0.274119 is one of those zeros, and then the other one is 3.5619. So 2 times. Show the setup, show the equations, and I did that right here. Letter C. During what time intervals is the bug moving left? I'm going to underline moving to the left and just remind myself that that represents when velocity is negative. So when is velocity going to be less than 0? So again, I've got my calculator. I'm going to look at the picture, the graph of velocity. So when does velocity maybe equal 0? And I actually have that mapped right here in Desmos. So here's a picture of the velocity of the bug, the graph of it, I should say. And it looks like I have a time right there at 1.733, another one here at 4.574. But because the question is asking for when the bug is moving left, I'm interested in when the velocity is negative. So here's my picture. The velocity is clearly below the x-axis, below the t-axis from the x value, or from the time of 1.733 over to the time of 4.574. And so that interval would be my solution to this last problem. So during what interval would it be? From the interval 1.733 to 4.574. Make sure that we round to 3 decimal place accuracy. And then because, how do I know that? Because the velocity is negative. And that would be a valid justification. So point totals here. Every FRQ is worth 9 points in your traditional AP exam. So I have 2 points up here in part A. I've got 3 points for part B. And a final 3 points here in part C. Oh, I apologize. Sorry, part 1 is actually also 3 points. Not 2. There's our total of 9. Okay. So that's FRQ number 1 with the calculator. I'm going to go to the next one in the same video here and just continue on. Here's a brand new problem. It says f is a twice differentiable function, and they have some given points right here. And they also define function g. G is the composition f of x. So letter A. Explain why there must be a value of c such that f of c is equal to 3. Now, whenever I see questions like this, I'm thinking about my big theorems in calculus, IVT, MVT, Rolle's theorem, EVT, the extreme value theorem. So let's kind of think about what theorem might help me prove that f of c is going to actually equal 3. Well, notice that f of 2 is equal to 7. F of 7 is equal to 2. At some point, if we have a continuous function, the function must have hit 3. And so that is beginning to sound like the Intermediate Value Theorem, IVT. But I can't use that unless I know that the function is continuous. Well, notice this. F is a twice differentiable function, and differentiability implies continuity. So f is continuous. F is differentiable and therefore continuous. And I'll say that f of 7 is less than 3. 3 is the element in question, which is less than f of 2. So therefore, by IVT, there must be a value on the interval 2 to 7 such that f of c is equal to 3. Let's look at letter B. Kind of similar here. Explain why there must be a value b such that f prime of b is equal to -1. Now notice the difference here. This is simply f of c. I'm trying to prove the existence of a function value. I'll call that just a regular function value. And when that's the case, it's going to be an IVT situation most of the time. But when I'm asked to prove the existence of a derivative value, prove a derivative value. Well, that's going to be the mean value theorem. Use MVT in a case like that. Now, MVT I can't use unless I know that my function is both differentiable and continuous. Fortunately, that was given. So f is differentiable and therefore continuous on 2 to 7. Now, MVT needs to have a difference quotient along with it. Let's check out f of 7 minus f of 2 divided by 7 minus 2. Does that difference quotient equal this element in question? If I get a match, then my answer is yes. Let's take a look. F of 7 is equal to 2. F of 2 is 7. and it looks like I'm going to have a -1, and there's the exact match that I have. So that difference quotient must be present in your formal proof of MVT. So in conclusion, I'll say by MVT, make sure you state the name of the theorem, there exists a value B on the interval 2 to 7 such that f prime of B is equal to -1. There's a mean value theorem proof. Letter C, next part of this problem here, says to show that g prime of 2 is equal to g prime of 7, and then to use that result to explain why there must be a value k, such that g double prime of k is equal to 0. So kind of a lot going on here. Let's just sort of tackle this at the beginning. Well, g prime of x, don't do anything with the 2 or the 7 until you first establish what g prime of x is. And so I'm going to use chain rule right here, derivative of the outside, inside stuff left alone. And then don't forget the chain rule times the derivative of the inside. So a lot of f's and f primes in there. So g prime of 2 is equal to f prime of f of 2 times f prime of 2. And that is going to become f prime of 7 times f prime of 2. Let's try that again with g prime of 7. Plug in a 7. And we get the same thing. So there it is, f prime 7 times f prime of 2. So you can check that off, show that they're equal. We just did. But then how does that help us here? Well, this again, a second derivative, so that's going to probably be an MVT situation. I want to prove the existence of yet another derivative. So g is differentiable and therefore continuous on 2 to 7. So let's check the difference quotient now. G double prime, well, that would mean I want g prime of 7 minus g prime of 2 divided by 7 minus 2. There's my average rate of change of g prime, which is my g double prime derivative analysis. But wait a minute, we just said that that g prime of 2 and g prime of 7 are the same, so I basically have a numerator of 0, meaning that entire difference quotient is going to go to 0. And that's exactly what I was trying to prove. So conclusion, we'll say by MVT, there exists a value k on 2 to 7 where the second derivative, g double prime of k, is in fact 0. Okay, and closing here up with another proof. So this one's heavy with MVT, IVT. Let's look at letter D to end. Another function h, explain why there must be a value r, such that h of r is equal to 0. Well, let's see. H of 2 is f of 2 minus 2, or 5. And h of 7 is f of 7 minus 7, or negative 5. Notice this, to go from 5 to negative 5, I've got to cross 0 somewhere because h is a composition of continuous functions. Itself is also continuous. So since h is continuous and h of 7 is less than 0, my element in question, which in turn is less than h of 2 by IVT, the Intermediate Value Theorem, there exists a value which we'll call r on the interval 2 to 7 such that h of r is equal to 0. All right, so let's go back and give some point totals here. Letter D was a 3-pointer. Letter C also a 3-pointer. So there's 6 points. We'll backtrack to parts A and B. B was worth 2, and then the opening problem there was just 1 for my grand total of 9. So I like FRQ2, just a collection of IVT, MVT problems, and those are 2 sample test questions that will hopefully help you prepare for this year's AP Calculus exam. As always, thanks for watching, and good luck with all the rest of your work.